The next concept we're going to look at with regards to momentum is impulse. And if we think about a collision, so I'll start off with that scenario, we've got a change in momentum. So the final and initial momentums of a given object, so we're not talking about the whole system here, we're just looking at one of the objects that's involved, is going to give rise to a change in momentum. So final initial momentums of an object, or one of the objects, is going to result in a change in momentum, and that change in momentum is otherwise known as impulse. So the concept of impulse itself is really just the change in momentum. Now this this quantity can be represented a few different ways. This one is actually not in the data booklet, but the concept of momentum, of impulse still needs to be understood as one of the content descriptors. So if we look at change in momentum or impulse, in some texts you might see that it's written as an I. I'm just going to continue to use delta P. So change in momentum is simply the final momentum minus the initial momentum. We can then expand that and look at the fact that the final momentum would simply be mass times final velocity, mv, and the initial momentum would be mass times initial velocity, mu. And so the change in momentum, or the impulse, could then just be calculated by looking at mass multiplied by the change in velocity, so v minus u. So we could use that as an equation. One of the really interesting things here, though, is that if we compare that back to Newton's second law. So from Newton's second law, we've got that F is equal to ma. And if we take that a step further, the acceleration that we're really dealing with there is a change in velocity over a change in time. If we consider that change in velocity, that would be v minus u on t, and hopefully you can see where this is going. If we then just slightly rearrange that, or even rather than keeping that m out the front, just chuck the m over the top there, you can see that on the top we now have the change in momentum, or the impulse. So we can instead write that as delta P on delta T. Sorry, that should have been a delta T there as well. So the force of a collision can actually be calculated by considering the change in momentum and the time over which that change occurs. Alternatively, we could write that the impulse, or the change in momentum, is equal to the force multiplied by the change in time. So in other words, if we the impulse that we're going to look at in an equation, in a collision, making a few mistakes here, impulse is going to depend then on the size of the force or the magnitude of the force and the duration for which it's applied. So I want to consider a situation here just to sort of make a lot more sense of this idea of impulse. So a specific example, if we think about a car coming to a stop, from a speed of 60 kilometers per hour. Now, in that situation, the initial speed is 60 kilometers per hour. The final speed would be 0. So the time over which the force is being applied now becomes particularly important. For example, if we're stopping at a set of lights, So that means that brakes are being applied to slow the car down. In that situation, delta t is relatively long. So it might be a braking period of say 10 or 15 seconds or even longer. So that means that the force that's being applied is relatively small. By relatively, what I mean is to compare that to a situation where a collision occurs. So in a collision where the car is travelling at 60 kilometers per hour, delta t is going to be really quite short. So the time for which the car comes to a stop is now extremely short, and so that means that the force is relatively large. So obviously if you're coming to a stop, you want that stop to be occurring over a long period of time, so that the force that's required to cause that change in momentum will be quite small. If you think about collisions where you've got a very short period of time, we've got a number of safety devices in cars like seat belts, airbags and crumple zones that are actually designed to slow the driver just over a slightly longer duration. So it might not be significantly longer, it might only be sort of a doubling of the time of the collision. So we might be talking, say, a matter of milliseconds. If you double that change in time, you're actually going to halve the force, and that can have a significant impact on passengers or the driver of the car. So rather than having the driver, say, their head hitting the steering wheel, where the change in momentum would occur over a very short period of time, by having an airbag, it slows them down over a much longer time comparatively, and as a result that force that they would experience would be much shorter, and it might be enough that it's going to save their life from or save serious injury. We'll have a bit more of a discussion about those ideas of seatbelts, airbags and crumple zones in class.